So my name is Ryan, and I'm a software engineer that works for Cubos. We are one of those new space companies that Steve warned you about Tuesday night or Tuesday afternoon. So the name of my talk is Bringing Full Stack to Small Sats. And I believe that the title of this talk pretty well describes what I've been working on this year and kind of what the mission of Cubos is as we approach small sat software. So I want to talk to you guys a little bit this morning about what we're building. What is this full stack? What does it mean for small sats? Why would we build something new? What's our motivation? What else is out there? How are we building it? We'll get a little bit into the architecture and design that we've chosen to go with. And then why should you care? Why does this project matter to you? So what is full stack? It's a term that's kind of come out of the web world, and typically it describes the layers of software that you need to stand up a website. So web server, database server, backend code, front-end code. All these things are needed to stand up your Google or your Facebook. Today, I want to kind of change that in the context of small sats. So here, full stack will refer to all the software that you need to stand up your payload or your science application, whatever it is, on the satellite hardware that you've chosen. So your operating system, the different abstraction layers that will be built on top of that, and probably some form of middleware. And then on top of all that will be your user application. What Cubos is doing is we are approaching this and we are trying to assemble a open source collection of software that will constitute this full stack, and it will run on any satellite hardware platform that we've given support to. So the idea is that your application, whatever it is that you're writing, it sits on top of our stack and it doesn't really know or doesn't really care necessarily what hardware it's running on. It kind of defers responsibility to the layers below that. So why do this? Why build something new? Well, when we took a look at the satellite or the state of software for small sats, we found that it was pretty lacking in terms of these full stack solutions that could easily float between different hardware and different operating system platforms. There's a few vendor specific ones out there, but they're pretty heavily tied to either the hardware or the OS that vendor is providing. We just didn't find very much in the way of generic full stack platforms. There are some good generic options out there. CFS is a great one, but even CFS lacks the operating system layer. That's still up to you to go out and find, and hopefully with some form of hardware support. We've chosen to build our stack in the open. Some of the software that we build is ours, and some of it we borrow from the open source community. So why do this? We believe that small sats and open source really go very well together. The small sat industry is moving in a direction of trying to enable rapid innovation and just really giving people a chance to get to space that haven't been there before. We think that building our software out in the open gives people a chance to, freely build on it. Even if they don't use the software that we've built, it's very easy to see the problems that we're trying to solve and the ways that we go about solving them. We develop all on GitHub, so you can see the conversations that our developers have as we work through different things and settle on final solutions. There's even the opportunity for the greater community to join in the development of our software. Anyone can join one of our pull requests, make comments, make suggestions, or even just look and see, the process that we're going through. So what's the current state of open source for small sats? Obviously CFS and CFE, they're at the top of the list. And frankly, I didn't really know very much about CFS before this week. And I'm so glad I went to the first day, which was all about CFS, because I was blown away by the work that's being done there and just really inspired because NASA has seen a lot of the problems that we are trying to set out to solve, and they're going about solving them in a lot of the same ways. So it's been really, really neat to see that. Cosmos is another fairly popular open source platform. Now Cosmos is just a ground station platform made by Ball Aerospace, but it's still really cool to see that out there for anyone to use. Another interesting project to look at is the UpSat project, which is made by the Satnogs guys in Greece. So UpSat, if you haven't looked at it, is pretty cool. It's a CubeSat, but all the hardware design and all the software is up on GitHub. So they call it the first fully open source CubeSat, in that everything is there. You can download the Eagle files, print out the PCBs, buy the components, then download the software from GitHub and flash it, and then you have their CubeSat that they designed. What I've seen kind of outside of that, and I want to give a shout out to RTIMS too, because clearly they're an open source OS, open source RTOS, which is very popular in this sector. So it's really cool to see the work that they're doing. Kind of outside of these projects, what I've seen as I've been browsing GitHub in the internet is that you will find a lot of either students or different missions that have taken their code and they put it up on GitHub, but when you start to dig into it, the code is like very tightly coupled to their mission, their hardware, their way of doing things. And it would be very difficult for someone to take this code and reuse it in any meaningful way without doing a ton of rework. I think in a lot of cases it would be easier just to read the code and then write your own based on the ideas that you get. But in a lot of cases you can't just borrow code. It's just so tightly coupled with what they've done. It's not designed with that in mind to be shared. And that's the thing that we want to go after, is designing to share and designing for other people to build on. All right, so what exactly how are we building this? So this is a high-level architecture of our current stack. So over here on the left, we have the application, which is your payload, science thing. You guys do all sorts of stuff that I don't even understand. So that's where those pieces go. I live more in the next two layers, which is the middleware. So these are like your common satellite services, things like telemetry, logging, commands, communications, common things that all satellites need that don't necessarily need to be concerned with the hardware, so we can build them in a more abstract way. And then below that, we have the portability layer. And this is the thing that lets our middleware and the application code live and run on any of the hardware platforms that we support. So let's look a little more into the portability layer. So this is made up of 3 different parts. We have the operating system, then the OS abstraction layer, which should sound very familiar, and then the hardware abstraction layer. For our operating system layer, we've decided to have a RTOS variant and a Linux variant. Right now we're using free RTOS, which is a open source available online RTOS, pretty widely used. And then we have Linux, which is another open source OS that maybe some of us have heard of. I think it's pretty widely used too. And this is the layer that sits directly on top of the hardware. So when we go about making support for a hardware platform, we actually publish the source that we use to port that to port these OSs to that hardware platform. So even if someone didn't care about the rest of what we've done, if they're interested in some OBC that we support, they could easily take the code that we've used to make FreeRTOS run on it and reuse that to make their code run on that OBC. So next we have the OS abstraction layer. And the idea here is that we want to take things like inter-process communication, threading, timing, and kind of abstract them away a little bit so that whether you're running on the RTOS or running on Linux, they kind of look and feel the same. Right now we're using a library called CSP. That stands for CubeSat Protocol. This was designed by GomSpace to be a communications tool, which we use it for in some places. But they also did a really good job of building in a portability layer, which we're borrowing right now as our OS abstraction layer. Now this will be eventually built out, I believe, to be kind of a POSIX compliant, much more full-featured layer, but that's still, it's part of the process. Building on top of that, we have our hardware abstraction layer. And this is designed to abstract away kind of the low-level peripherals that are pretty common to all the embedded boards out there. So GPIO, I2C, SPI, and UART. We're making clean, abstract interfaces for these things so that the code you write against them doesn't necessarily change, or the interfaces you write against don't change based on the platform that you're using. You can be more concerned with, all right, what pins do I need to work with? What data do I need to write in and out? But not so concerned with what's the name of the function that I'm using? What do the interfaces look like? So going with portability, I would be remiss not to talk about what we are portable on. These are the hardware platforms that we support right now. The first two, the Discovery Board and the Launchpad, are both dev kits. And the nice thing about these is that they are really cheap. Anyone could go buy one off the internet and start running our software really quickly. Both those run the RTOS variant of our stack. So this third one, the Nano Avionics SatBus 3C1, that is a CubeSat OBC, and that also runs the RTOS variant. And then this last one, the unfortunately named ISIS IOBC. This is a platform that's we're currently working on. This will be the first platform that supports our Linux stack. Okay, so building on top of the portability layer, we have middleware. And I just want to talk a little bit about telemetry. It's kind of the first service that we are developing, and it's still in the works. So this is kind of a high-level design of it. As we've approached telemetry and really thought about it, we've come to the same conclusion that I think a lot of people have, that telemetry is just a way to pass around data. So we're modeling it as a fairly simple pub subsystem. You have your publishers on the left side, so your data sources, whether that's like a sensor or some system value, or maybe even some other subsystem that also is running telemetry and wants to pipe some of its data back to the OBC or to the COM board, wherever. Then on the right side, you have your subscribers, so could be your beacon, could be some storage system, could be a health checker. I mean, really, it doesn't matter. Whatever it is that's interested in the data, that's one of your subscribers. So the telemetry ends up being just a data broker who keeps track of what data is coming in and who's interested in that data and publishes it out whenever it's available. So as we approach more middleware services, we want to take this really high-level design view and build these abstractions that will work across any operating system that we support and any hardware platform that we've built in support for. Okay, so our development environment. We have taken the approach of building, I'll call it a SDK in a box VM. And I've heard this come up several times this week, and it makes sense because it's just such a clean way of approaching the problem of packaging up your dev tools. So we have one VM that we distribute, and it's got all of our source for our operating system, our middleware, and for all the different hardware platforms that we support. We also include in there our tool chains for compiling, then tools for flashing and debugging. So you don't have to worry about polluting your host system with tool chains and all sorts of other tools. Just one VM that contains everything in it. Makes life much easier for us. This is actually how we do development in-house. My computer is not completely polluted by work stuff, it's just by other stuff now that I like to experiment with. But I can keep all of my work tools at one clean, sane state, thanks to this box that I develop in. Another tool that we use that's on there is Yada, and this is kind of the basis of our build system. So CMake has come up a few times this week, and CMake is really cool. Yada is like CMake for CMake. So what Yada does is it lets us split up our source into different modules, and then for each module we can attach some metadata in the form of JSON config files. And Yada will read in these config files and kind of determine, all right, what hardware are you building for? What OS are you building against? And it will then generate the appropriate CMake files to pull in the source for that, which then will generate the appropriate make files to actually do the compilation. So it lets us have a pretty cool module system that we can tag with different OSs and hardware, and I don't really have to worry about manually specifying those dependencies. I just tell Yada, like, hey, I want to build Cubos for the RTOS on this discovery board. And it goes out through our module tree and figures out, okay, here are the modules that you need, here are the compile flags I need to give them, and then it builds it for me. So makes it super nice. Okay, so why should you care? What I think is that you shouldn't really care so much about using CFS or using Cubos. I think that what you should care about is the problems that we are trying to solve and the solutions that we are proposing to these problems. CFS exists for a reason, and Cubos exists for a reason. And those reasons are real problems with software reuse, with collaboration in software, with being able to see what's going on in the software that you're using. So I think it is worthwhile to consider those problems and to consider the different solutions that are being proposed to them. And whether you use a pre-made solution or decide to roll your own solution, I think that's up to you. But I think that, you know, what's really important is just to see, okay, do I have these problems in-house? Am I choosing just to live with them? Or is there something better I can do? You know, is there some better way that I can be developing my software? All right, that's all I got. Any questions? Here. You gonna ask me what language we use?
Yes, I am.
Okay.
I think I know the answer to that, but I'll have a follow-up to that.
So we use C.
Okay, and why do you use C?
Why do we use C? Well, probably because that's the language that most of the engineers at our company know, and because that's what FreeRTOS is written in and Linux is written in. It's just a good common denominator right now.
What do you do about the high error rate in C software?
Right now, code reviews. It's a thing. Testing is definitely something that we are working into. We're building up a CI system so that every time we push code, it gets pushed out and tested against all of our platforms. that's very much a system in the works right now.
Have you considered other languages that are more reliable?
So I would like to consider actually using Ada at some point. I think it's kind of a matter of getting buy-in from other people and then, kind of weighing the costs and seeing, okay, where would that really benefit us versus just flat out converting everything to Ada.
Thank you. Loaded question here. Do you have unit tests and 100% coverage built into your SDK in a box yet?
Built into our SDK or our source code?
Oh, in the box. So if I were to download your VM, would I be able to run 100% unit tests and coverage?
No, not yet. One day.
Are you working there?
Yes.
Cool.
Other questions? No? Thank you.
Cool.